Hello students, welcome back. Let us talk about problems 21 and 22 from section 2.2. And here's the problem. Let A be a square matrix. Prove the following claim. And first part is this. A squared is a zero matrix and I minus A is invertible. Next, A cubed is zero matrix, then I minus A is invertible. In general, a to the nth power, where n is some positive integer, like a to the 15th power is zero matrix, then I minus a is invertible. So C is the most general case, and if you can do C, then of course A and B follow. How do we prove a certain matrix is invertible? Let's start from there. A matrix B is invertible if the inverse matrix exists. If B times the matrix C happens to be equal to C times that matrix E, basically this is what you have to do. You see, what you need to do is finding this matrix C, which I'm highlighting in red. So that is the inverse matrix. So if you have to prove something is invertible, don't try to do anything to the matrix itself. You have to find another matrix so that B times that, another matrix that original matrix times that matrix is equal to I. And of course, vice versa. If you do one, the other one is going to be easy to do. So usually I'll just do one and then leave the others to students. So how does this thing work? Let's see. We must prove this. This matrix I minus A times something is equal to I. This is what you have to do. Oh, as a matter of fact, that's not enough. Excuse me. That something times I minus A is equal to I. Oops. Wrong key. But if you do one, the other, it's going to be easy as a matter of fact. So the key is just finding certain matrix so that the matrix times the original is identity matrix I. So don't try to meddle with this part. Okay? Don't try to do anything with B, this B part. The key is to find this one. How do we do that? Well, let me give you just a little bit of hint. We have to use this a squared is equal to 0, or a cubed is equal to 0, or a to the nth power equal to 0, right? Okay. And how does it help with this I minus a? Well, here's another hint. Recall this algebraic rule. So x to the nth power minus y to the nth power is equal to x minus y times x to the n minus first power y to the 0 power plus x to the n minus second power y to the first power x to the n minus third power y to the second power. And I got a little bit tired of it, so let me use dot dot dot, and then let's conclude. X to the first power y to the n minus second power, x to the 0 power y to the n minus first power. Okay, that's it. Please note that the powers add up to n minus 1 all the time. And then one more power here. So total power is going to be n for each. By the way, if you're wondering why this is true, you can prove it from the right-hand side and then just break up the parentheses using the distributive property. And you'll see a bunch of cancellation. Pluses and minuses canceling out, boom, 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 boom. And you're going to get only x to the nth power minus y to the nth power. Everything else in between canceling out. So this is actually true. And use the matrix version of this, and you're through. Excuse me. You want I minus A, so let's reverse the order. Would have been okay. I only need this negative sign, but well, the problem said I minus A, not A minus I, so let's rewrite it like this. Zero power, by the way, is 1, so in matrix version, zero power is going to be identity matrix I. So what do you have? I to the n minus first power, that's also I. So this is I. Okay, all right. Let me take just one more step. So this is equal to I minus A. And then I plus A squared plus A cubed plus da 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 da. It goes up to n minus first power. You see, this is I, that too is I, and then all the i's over here, those are identities, so they just disappear, and all I get is zero power, first power, second power, third power, all the way to n minus first power. And this will be helpful. This will be helpful. By the way, this expression here, this thing is actually very important. It's so important it has some formidable name. It's called cyclotomic. And what is cyclotomic? Cyclotomic polynomial? It's going to be an important topic in abstract algebra. Let's stop there. And I believe everybody here will be taking abstract algebra, so I'll just leave you there. And as for this factorization formula, it appears a lot here in this course, but also in number theory, and of course, abstract algebra 1 and 2. As for cyclotomic polynomial, maybe it appears in abstract algebra 2, not in abstract algebra 1. It's been a long time since I taught abstract algebra 1, so I'm not exactly sure whether it's in there or not. Anyway, as for the importance of these factorization formulas, they are moderately important for this course, but for number theory, it's extremely important. And they're going to do some role here for this problem. Okay, all right. How about this one? Let A and B be square matrices with the same size. We say A is similar to B. A is similar to B if there's an invertible matrix T so that this. B is equal to TA T inverse. And T only have to exist. So if you have different T here, it's okay. And this matrix T is called transition matrix, and it is related to a change of coordinate, but I don't know whether that kind of thing will appear in this level. I mean, our textbook author discussed it, but he buried it at the appendix after chapter 4, so I don't know whether I'll have time to cover it or not. But the similar matrix concept is something we can handle, and it's important. And it's gonna show up again with vengeance in chapter 8. So let's talk about it here. Suppose that A is similar to B, then B is similar to A, which means that A is equal to something B, something like this. And what do we put here? And the same thing, of course, here. Well, that's something we have to figure out. And I'm not going to give you too much here. I think I already gave you too much. In any case, the structure should be that. The letter T is not that important. You see, we only need an existence, certain matrix T. Whether I use T or P or some other character R, it doesn't really matter. As long as we have something and that thing inverse, we have similarity there. So if A is similar to B, then B is similar to A. Next, if A is invertible, then B is invertible, and vice versa. Well, let's see, what do you mean by invertibility? What do you mean A is invertible? That means A times something is equal to I, right? Does it mean B times is equal to I? Of course not. B times something else will be equal to I. So it doesn't matter which one it is, but something exists here. And then some other thing exists here. That's all there is. So A times some matrix, which we'll have to figure out, is I. Excuse me, what am I talking? You don't have to figure it out. This is an assumption, and this red part is something you have to figure out. So assume A times something is equal to I, okay? And then figure out this part. B times some other thing is equal to I. So because this part is just, something you can name, it's okay to use another character, like, let's say C. Okay, all right. And your job is to figure out this part. It's gonna be some C expression, but also you'll have to use this. B is T times A times T inverse, that one. Okay, so figure this one out, and then that's about it. Of course, you have to prove the other way around, but you have one, then going the other way is very similar, no pun intended. I mean, the methods are similar. Next, transpose are similar to each other. A transpose is similar to B transpose. Okay, I'll just leave that to you. No, not really worth it. I guess that's about it. Good luck, everybody.